The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everybody. Welcome to Unlocking the Black Box, exploring turbidity data integrity at water treatment plants. This is the first of 3 webinars we're going to be hosting on data integrity. I'm Anthony DeRosa with ASDWA, and our presenters today are Nancy Fagan and Steve Deem of Washington State Department of Health. And without taking up too much time here, I'm going to kick things over to Nancy and Steve, and we'll get things going. Just a couple of quick logistical issues. If you have any questions, you can enter them at any point during the presentation using the questions panel on your webinar control panel, and we will do a Q&A session at the end of the webinar. I am recording the proceedings, and we'll have those posted to the ASDWA website in the past events section. It's just a subpage of the events section on the ASDWA website, and I should have that available tomorrow. And that will be a video recording along with the slide deck. If you have any questions, feel free to email me about the logistics. And with that little intro, I'll pass things over to Nancy and Steve. Thank you, guys.
Good morning from here in the Seattle area on the West Coast, and good lunchtime and good afternoon to all of you across the rest of the country. This is the voice of Steve.
And this is the voice of Nancy. We want to thank ASDWA for hosting this series of 3 webinars covering data integrity. As Anthony mentioned, this first one covers turbidity. The second webinar will focus on disinfection data integrity and will be held in 2 weeks on Monday, January 22nd. The third and final webinar will include a brief recap of findings from the first 2 presentations, and will focus on implementation issues from a state regulatory perspective. Since the third webinar is intended for states, ASDWA has sent out a separate registration link to its members for this session.
Many people think of a flight recorder when they hear the term black box. And these black boxes for planes and trains are usually bright orange, they're not black. These flight recorder black boxes receive multiple data inputs that are stored in the device, but rarely, if ever, get accessed or used to operate the plane. We are referring to the term black box in its abstract concept, denoting a device, a system, or object viewed in terms of its inputs and outputs without knowledge of its internal workings. We want to share our exploration into the black box of turbidimeters and associated controllers that began with a year-long study of 25 rapid rate filtration plants treating surface water supplies in Washington State. Over the next 59 minutes, we will present findings and conclusions from that study and continued efforts toward improving turbidity data integrity used in the drinking water world.
Our drinking water program in Washington is part of the state health department. We recognize that partnerships are vital to our success. We work with water utilities, local health jurisdictions, EPA, other state drinking water programs, and ASDWA, who's sponsoring this series.
Washington has a population of just over 7 million residents. Nestled next to the Pacific Ocean, and Canada has a diverse geography and varied climate. The Cascade Mountain Range bisects the state into a marine-influenced moderate wet side and a drier, more variable temperate east side. 70 degrees is considered a hot summer day in Seattle, while hot summer days in the Tri-Cities on the east side can easily exceed 100 degrees Fahrenheit. Mountains in the ocean create some extreme rainfall differences too. The Hoh rainforest on the Olympic Peninsula gets 140 to 170 inches of rain a year. That's 12 to 14 feet of rain. And just 50 miles away, the town of Sequim in the rain shadow of the Olympic Mountains averages 17 inches of rain annually. And way over on the east side of the state near Idaho, one of our wine growing regions, the town of Walla Walla averages 18 inches of rain a year. So this diverse geography and varied rainfall patterns create a fascinating mix of drinking water sources here in our state. Groundwater sources include all manner of springs, high production alluvial wells, wells finished in fractured bedrock that are drilled without well casings, and some low production wells with yields measured in gallons per day. The combination of low rainfall and low production wells have even spawned the use of seawater reverse osmosis sources in our offshore islands. Surface water supplies include mighty rivers like the Columbia River, draining vast areas, pristine river and lake sources up in the mountains, low alkalinity snowmelt, tiny ponds that look more like wetlands, and flashy streams with variable water quality.
Surface water is an important source of drinking water in our state. Over 60% of our citizens receive drinking water from a surface water source. In addition to disinfection, surface water treatment facilities in Washington use a variety of filtration technologies to assure safe drinking water. As you can see in this slide, rapid rate filtration is the most common technology, the most common filtration technology used in our state, accounting for about 45% of the total. The 25 utilities that participated in our initial project were all located in the Northwest region. That's the pink-purple area on the map. We had a huge variation in system size, everything from an 18-gallon-a-minute package plant to 132 million gallon a day municipal facility, and all of them used rapid rate filtration. We picked this group of utilities because with rapid rate filtration, turbidity is the single most important parameter used to tell that the treatment plant is working effectively. In terms of filtration treatment, success most often gets measured by turbidity.
Turbidity is a measurement of the clarity of water. Turbidity is caused by suspended and colloidal matter in the water. If we turn to one of the guiding books or our Bibles in the industry, Standard Methods, turbidity is defined as the optical property that causes light to be scattered and absorbed rather than the light to be transmitted with no change in direction or flux level to the sample. Turbidimeters with scattered light detectors located at 90 degrees to the incident light beam are called nephelometers, and results are expressed in nephelometric turbidity units, or NTUs. Turbidity monitoring is used for different reasons. It's used to determine treatment efficiency or performance, usually by monitoring turbidity reduction across a treatment unit. We are focusing on filtration, but sedimentation and contact absorption clarifiers also use turbidity to assess performance. Turbidity is used to ensure that turbidity levels don't interfere with chlorine disinfection. This concept is a primary reason behind the 5 NTU limit for unfiltered water supplies. And it's used to quantify disruptions in distribution systems. So for example, when sediment is stirred up in pipes from water main breaks or fire flows. So regulatory values. Several different ones. 0.3 is the maximum turbidity limit for rapid sand filtration. 95% of the combined filter effluent turbidity values must be below 0.3. 1.0 is the maximum value for rapid sand plants. Exceeding 1.0 results in a treatment technique violation. 2.0 is used for determining performance on individual filter effluent. And 5.0 is the maximum turbidity value for unfiltered sources and for other filtration technologies like sand filtration.
The 1993 crypto outbreak in Milwaukee, Wisconsin was a huge wake-up call to our industry. In the years since, there has been a shift beyond regulatory compliance to optimization. And this is in part due to research showing that systems can significantly reduce the risk of waterborne disease by lowering the turbidity of the water that they produce to less than 0.1 NTU. So as you can see in this graph, dropping the turbidity below the regulatory limit, which is the dashed red line, to the optimization goal of 0.1 or less, the black line, improves the removal of cysts like Giardia and crypto. So EPA responded to the outbreak, of course, by developing new regulations, but they also developed national optimization goals and created AWOP, the Area-Wide Optimization Program. This was designed to help states and water utilities achieve the optimization goals. In Washington, we adopted the low turbidity goal in 2003, and we started our treatment optimization program, or TOP, which includes a recognition program for utilities that reach the goal. We joined our local AWOP group in 2009, which now includes states from both EPA Region 8 and 10. Over time, the performance of our rapid rate plants has steadily improved, and the numbers of systems meeting the turbidity goals has roughly doubled from 32% when we started to 60% last year. 2 years ago, we reached a milestone. We had 4 systems in Washington that received awards for 15 years of consecutive optimized performance. The genesis of this turbidity data integrity project was an EPA data integrity workshop in October of 2012. It was held at a local water treatment plant, and it consisted of 3 teams spending the entire day looking at nothing but turbidity, from the sample tap through the instruments to the SCADA system, and finally to the report that gets submitted to us each month. This was a real eye-opener for me. I had no idea how many factors there were that could influence the data that we received. I returned to the office the next day and told Steve about what we had learned and found, and we started wondering,
wow, I wonder how accurate the data is we get from all plants every month.
So he and we decided to visit another treatment plant, and we learned more and we found more there. We decided to go to another one. And eventually, after the 4th plant, we decided, you know, we need to visit every single plant.
So the effort was born. A reminder that this effort started with a single question, led to inquiry, and then evolved into a research, studying, learning project. We took an interactive or adaptive approach. So as things unfolded, as we learned more, then we modified our approach. From the beginning, we started with an operator interview, and we wanted to look at written standard operating procedures, or SOPs. We looked at, of course, turbidity setup, maintenance and calibration verification procedures. We asked for and looked at maintenance logs, and frequently asked a specific question and then look for where that's documented. We wanted to physically touch equipment manuals, and then we looked at reporting procedures. And we used the monthly report that the utilities sent to us. We'd maybe pick a date and find out where those different values came from. So here's some of our data sheets. We look at the instrument location, and we would go to each instrument, look at the current reading, and then we would compare that exact same moment in time, what the SCADA or recorder was reading. So in some small plants, you can do that by just shuffling your feet maybe a little bit. In large plants, which are maybe minutes apart, we would use cell phones or radios to actually capture at the same moment in time what they were reading. All of the 25 systems used HOP products in this study, so we structured our forms to follow the controller logic path, and you can see some of the things that we looked for. Ideally, we had the operator access this information through the controller interface. And quite a spectrum. Some of these operators, not kidding, they're like Jedi Knights of the operator interface world. It's a blur. I can't see it, what they're doing, but they suddenly materialize at the right spot. Other operators, very uncomfortable touching the screen, frequently for fear that they might mess up a setting. We also looked at and measured directly meter flow rate through the turbidimeters, and then made note of different installation details.
At the end of each visit on our way home, I should say that Steve is kind of a efficiency nut, so we had to pack in everything we could, even into the drive home. So we would do a 1-page summary of what we had found. So the make and model of the equipment, how the utility was doing their reporting, some key settings that we thought were especially important, and then we would summarize other topics and things needing follow-up. And in the beginning, most of the follow-up was for us because there was a lot that we didn't understand. And after each visit, we'd have like a half page or more of questions about what we had seen and the equipment they were using. So we finished this in the car, we give it to our clerical staff the next day, and our goal was to get this back to the operator within 24 hours of our visit. So we have a lot of great operators, a lot of great plants in our state, and the majority of them were very much open to learning new things and very receptive to this project. So let's talk about some of the things that we found.
The error mode controls the value sent to SCADA or the recorder when a communication error occurs between the sensor and the controller. And there are two options, hold or transfer to a value. Both Microtoll and Hawk SC controllers have the setting. And the default setting for the Hawk controllers is hold the last good reading. So with this, if a communication error occurs when it's set to hold, the error will show on the controller screen as shown in this picture, but it will not show on the remote SCADA or chart recorder. So the instrument is no longer sending up-to-date information to the controller, but you don't know that unless you're at the controller in this setting. 100% of the treatment plants with the setting option had it set to hold. There's 19 systems. So we think that a better option or better mode is to set it to transfer, and we want this transfer mode, which value you're going to send it to let the operator know that something is right, but we don't want some unintended consequence, like an auto shutdown because you send it to a high alarm, or equally as bad, you trigger a regulatory violation. Because remember, the issue here is that the turbidimeter is no longer communicating with the controller. It's not necessarily that the turbidity itself is wrong.
The next thing we looked at was signal averaging. So this is a setting that reduces noise in the data by averaging individual readings. And the goal here is getting a stable enough reading so that you can detect particle events, trends, and breakthrough in your data. So the typical options for this are 6, 30, 60, and 90 seconds. If you look at the graphs on this slide, the one at the bottom basically has no signal averaging. And so in the moment, it's hard to tell when the performance starts to degrade and they get breakthrough. The upper one has signal averaging on, and you can see it's much more clear when breakthrough starts to occur. So the default value is typically 30 seconds. 6 seconds is intended just for calibration. If you go with one of the higher values, you're going to increase your response time. Here's what we found. 7 systems had turbidimeters set for 6 seconds. So they were seeing some erratic results. 14 systems were using the default value of 30 seconds. 1 system was using 60, and 3 had it set at 90. Now, the operators in general hadn't been involved in setting up their equipment, and so they didn't realize that these settings were there, and they didn't know why they'd been set that way. On the 90-second, we thought that was pretty long. So we tried an experiment with the filter offline. We lifted the turbidity sensor up off the body to simulate a high reading. And then we had the operator watch the SCADA screen to see how long it took for the high turbidity to show up there.
And 90 seconds is an amazingly long time when 2 people from the health department are standing over your shoulder watching a screen that doesn't move.
So we think the default value of 30 seconds is a good starting place for filtered water, and it seems to work well for most plants in our state. Another interesting thing about this is that this does impact the value that's shown on the controller screen. So if you're looking at a device and you see a lot of erratic readings, the first thing I would check is the signal averaging setting.
Turning to the bulbs on the turbidimeters, the tungsten bulb in the Hawk unit degrades over time, and this degradation speeds up over time. So Hawk recommends that bulbs be replaced at least once a year. I think of this as akin to replacing smoke detectors annually. 52% of the systems, the 13 systems, were not replacing bulbs annually. And there were different practices in play and different reasons at play for not replacing them annually. Listed some here. Some systems replaced the bulb when they were no longer able to obtain calibration. Some replaced it when the light went out. Some when it visually looked dim. There's some operators didn't realize that that was a recommendation from Hawk. And there was a couple like, we're just skeptical of these things like, you don't really have to do it. It's just another thing to get more money out of us. Turning to the smoke detector comparison, we think it's probably better to replace your batteries on a routine basis instead of waiting to find out your smoke detector doesn't work. So in the turbidity world, if you wait to replace on failure or until you're unable to achieve calibration, then that can result in the unit not holding the quarterly calibration. So it's something you'll probably hear from us a lot. I think you have to follow the equipment manufacturer's recommended maintenance schedule in most cases. Calibration and verification are critical operations for turbidimeters. In Washington State, online instruments must be calibrated using a primary standard at least quarterly if they have an incandescent light source, and annually with a laser or LED light source, unless the manufacturer recommends more frequent calibration. And must be calibrated after performing maintenance on the unit. So maintenance such as cleaning the photocell or changing the lamp can affect readings. In addition, continuous online instruments have to be verified at least weekly using a properly calibrated benchtop unit or a secondary standard such as the Hawk IcePick 20 NTU. So looking at primary calibration, 100% of the systems were calibrating at least quarterly and documenting the results. Now we realize that you can't really get above 100%, but this actually feels like more than 100% because in 1991, our department in a statewide survey of 171 systems in Washington found less than a third of the turbidimeters had been calibrated with a primary standard within the past year. So this is a big woo-hoo. Clearly, you can't get any better.
So Steve mentioned that our state rules require a weekly verification of each online analyzer against a benchtop turbidimeter. So this is the requirement, and it has two purposes. First is to just verify the instrument between those quarterly or maybe even annual calibrations. But second, we want our operators to maintain proficiency with their backup turbidimeter. So usually you'll find the benchtop will read higher. We consider a good verification to be within 10% or plus or minus 0.05 when turbidities are below 0.5 NTU. So we found that almost 2/3 of our systems were not verifying their online turbidimeters. And this was the most common reason why. My benchtop never matches the online instrument. So let's take a look at that. Here's an experiment or exercise that you can do to see what's happening with your results and to prove to yourself that good technique actually matters. So you start out with a properly calibrated online and benchtop instrument, and you take a grab sample and put it into the oldest, most scratched sample cell that you can find and take a reading. Then you change to a new sample cell and you wipe your hands all over it and take another reading. That's going to be your baseline. And now, step by step, improve your technique. So let me show you what happened when I did this. So I started out and the online meter was reading 0.03 NTU. With the scratch sample cell, I got what's that, 15 times the reading, 0.47. Then I switched to a new sample cell, but I wiped it off with my hands, and I dropped the turbidity in half. Then I cleaned the sample cell with deionized water and a lab wipe, and it dropped in half again. And then I applied a small amount of silicone oil, rubbed it on, wiped it off, and now I was down below 0.1. And then I tried orienting the sample cell, and I got it down to 0.08. So that's a good verification within 0.05.
When we talk about verification, we're usually talking about grab sampling and this difference between the grab and the online. So I just want to review a few of some of the common problems we've been finding. One is obsolete or non-functioning meters. Wow, our industry, I think probably especially operators, we're a frugal group. They want to get the most out of all the money they collect from people and use to run these plants. And sometimes they may be holding on to equipment a little too long. Not properly calibrated, another common problem. Back to the frugal nature of the scratch sample cells is tough, so buy some new ones. Dirty sample cells, this is really your technique that Nancy just went through. Stray light can be from poor technique or even broken equipment, and then bubbles. Bubbles, we think, can play a big role. So here's some tips, I think, to improve that. And look at degassing your grab sample. So let it sit for several minutes with a loose cap. Avoid condensation. Remember that the benchtop units are shining light, right? We're shining light, and they're going through glass and water. So there's two interfaces there. If you have condensation, you're essentially adding another barrier, not barrier, but another place where light can be diffracted. The online instruments don't have that extra glass step. A little bit of silicone oil can be quite useful in reducing the condensation. And then correct location. And in this case, correct location is we want the exact, or as close as we can, same water that the online instrument is measuring. This is a different issue from, are we sampling in the correct location for determining turbidity through a filter? When we're looking at verification, we want the same water as the online instrument. So let's take a little closer look at that, where that right spot is.
So most of our systems had 1720D or E turbidimeters that look like this. So you have basically three choices. You can take the sample from the service drain, but usually that would cause a lot of sediment, so that's not a good one. You could go with the sample inlet right there, or you could go with the sample drain. So the sample inlet is before the bubble trap. So if you have bubbles in your water, that's not the best place. You can also cause some disruption in the flow that can impact the reading. So we think that the sample drain is actually the best place to take the grab sample. Number one, because it's gone through the bubble trap, and number two, because you're not going to disturb the flow of the sample, provided that you have this all set up right. So we like to see an air gap here. This is an example of a commercial attachment that you can buy, but I'm sure you could make something like this. So right in there is the air gap, so you can get your sample bottle in there to collect the sample. You can also visually see that you have flow going through the turbidimeter, and that's a location where you can sample the flow rate or measure the flow rate to make sure it's within the manufacturer's specification. This is an example of a microtol. We have a few of these in our state. They do not have a bubble trap, but if you want to use the air gap type location, then that would be on the drain tubing that we've circled there in red.
The human component of data integrity at times may be the most important factor. It's be hard to quantify that. One of the things we think is how you set up for maintenance and verification practices plays a huge role. This is a photo at the Everett Water Treatment Plant, and this is how it should be. The instruments are at eye and shoulder height, so easy access. you notice that they put a shelf here, a work shelf, to put your equipment down and do proper practices. You can do your verification, put your benchtop unit down here. Looking at documentation for that verification check, also very important. This is actual form used by a treatment plant. They have 3 filters. If you look here, they go on a weekly basis. They read their SCADA reading and compare it to their online meter reading and record those values. And then they have a grab sample, and then they mark it, yes or no, is it within 0.05 or not. So here we're filter 2, the SCADA and online match, but the grab sample is significantly different. It's out of spec. So down below, they mark now, well, what do you do if you get a difference greater than 0.05? And in this case, filter 2 was recalibrated on the date and passed. So sample flow rate is specified for all continuous instruments. 200 to 750 mils per minute for the 1720B. High flows give you a quicker response, and high flows plus cold water could get you bubbles, so that might be an issue. Greater than specifications may lead to overflows and incorrect readings. What did we find? 70% of the systems had at least one instrument outside of the manufacturer's specified flow range. Now, most operators know there is a specified range. A few don't know what the range is, but they know it. We experienced or found a wide variation in measured flows, both above and below the value. And I think a lot of that has to do with the eyeball method. And so this is where you look at the water flowing out of a turbidimeter, and through a complicated algorithm in our brains, we come up with a flow. This, of course, prompted some pretty good-natured challenges almost from the get-go. So we went with all 3 of us guessing, I guess it's guessing, but then measuring it to the actual flow. And really, no one could match the measured flow is what we found. There are sometimes issues with variable flows coming from changes in filter head. So this this could be fixed by putting in a constant head tube on the front end of your turbidimeter. The main takeaway is you have to measure and document on a routine basis. Lots of questions about, well, what is the best number? We think that 500 mils per minute appears to be a good starting point. A flow may need to be reduced if you have air bubbles, or if there's a problem with water conservation at the treatment plant in question.
One of the most important settings that we looked at was signal span. Most of the finished water turbidimeters read in the range of 0 to 100 NTU, and the signal span is the range of turbidity values that get sent to either the chart recorder or SCADA. What you want is a balance between range and resolution. You need to be able to detect regulatory limits, the ones that Steve mentioned early on. But you also want to have good resolution so that you can be an optimized plant. So here's what we found. All of our plants had the lower level set at 0, so 4 milliamps set at 0. But there was actually a huge range in the upper limit, and these were all for finished water turbidimeters, everything from 0.5 to 100 NTU.
Which is not much of a filter.
That's right. So an interesting thing about signal span is that it changes what goes to the controller, but it does not change, it changes what goes to SCADA, but it does not change what you see on the controller there. So that's an interesting little fact. Here's an example of where signal span can be an issue. We still have some small water utilities that use chart recorders. This is a 10-inch chart recorder paper from a small town. And you can see here, if you have the signal span setting at 0 to 100, then each of those tiny lines there is 1 NTU. That would be your entire, you couldn't even tell if you had exceeded the 0.3 turbidity standard. If you had it set it from 0 to 10, then each of those tiny marks is 0.1 NTU. So for an optimized plant, the pen would just go between 2 lines for the entire time. And even if you had 0 to 5, each line would be 0.05 NTU. So this is makes it hard to use a circular chart without, to get the resolution you need, but not to be able to detect a regulatory violation. So I'm going to throw in something I didn't before, which is that a lot of these instruments have 2 outputs. And so you could have 2 pens on this chart and have them set at different resolutions. So you could capture the normal operation and also if you ever had a regulatory violation.
When signal span is too small, this leads to something called data capping. So in this first picture here, you'll see that we were looking at data from combined filter effluent, and they're in a filter run at 0 at midnight, and they're running along great. They're optimized. They're below 0.1. And around 14-24 hours, their coagulant feed pump clogs, and turbidity jumps up, and in fact goes above 1. And then you can see they're out of control, and they continue on in trouble. If they had their output set for 1.0 equals 20 milliamps, this same excursion shows up differently in the SCADA system. So in this case, they're still running along great. Their coagulant feed pump still clogs, but now turbidity somehow miraculously is held at 1 and then bumps around, still out of control, but never exceeds. We found 72% of those systems, or 18 systems, had signal span set to cap the maximum turbidity sent to the SCADA system or the recording device at a level below the regulatory limit. Most of these cases, they were set to 1.0 NTU, but we also had one set at 0.5 and another at 0.6 NTU. So that's not so good. The common reason for setting at 1.0 is, well, they never go above 0.3 NTU, which is great, and that's exactly what we want. But we must be able to capture if something goes wrong. It's a regulatory requirement, and also quite helpful in troubleshooting and perhaps trying to assess the magnitude of the event to be able to capture above the regulatory event. So we have some tips for that. At rapid rate filter plants, a reminder that the individual filter effluent must be able to detect and record values above 2.0, and the combined filter effluent must be able to detect and record above 1.0. So we think a signal span of 0 to 5 NTU works well for these rapid rate plants and other technologies where maximum turbidity limit is 1 NTU. A signal span of 0 to 10 could be used or should be used for unfiltered systems, or with technologies like slow sand filtration, where the maximum turbidity limit is 5 NTU.
Steve mentioned that almost 3/4 of the plants were capping their data below a regulatory limit. Some of our operators were reluctant to increase the span because they were concerned about resolution. They were trying to be optimized. They wanted to have really good resolution. And so we put in this slide to help answer that issue. So resolution is dependent on 2 things: the span that you set in the controller and the type of processor inside the turbidity sensor. So if you think about an older turbidimeter like a 1720C, and we did see a few of those in our project, it has a 12-bit processor, and we're talking about setting the signal span from 0 to 5. So you put those values into this equation, so 5 divided by 2 to the power of 12, and you can see that the resolution is 0.00124. So we're talking here the third digit. If you had a 16-bit processor like is in the 1720Es, we're talking the fourth digit, the fourth decimal place. So the conclusion here is even with older turbidimeters, a signal span of 0 to 5 will still give you plenty of resolution for meeting optimization goals. Okay, let's look at some of the other findings. We had some larger plants had many filters, and we found inconsistent settings between the instruments in almost half. We're thinking maybe this was because replacement filters or replacement turbidimeters were brought in, and they didn't get set up the way the original ones had. No maintenance logs. So we would ask a few questions about, for example, when was the lamp replaced the last time, and if the information was readily accessible, then through a maintenance log, then we counted that as a yes. So we found about 40% didn't have a readily accessible maintenance log system. Standard operating procedures for the instrument setup. So take a look at this, almost 100%, but not quite. 92% of systems had no standard operating procedures describing the settings that they had for their instrument.
We think that lack of those written SOPs for setup is a primary cause behind a lot of the inconsistent findings or settings that we found and weaknesses in data integrity.
Thanks for pointing that out, Steve. So standard operating procedures, what do we mean by that? So it's a tool to ensure that everyone does it the right way every time. So they need to be written down, they need to be up to date, consistent with industry best practices and the manufacturer's instructions as well, and aligned with regulatory requirements. So here are some tips. They don't need to be overly bureaucratic. They can be as simple as you want, but you want to make sure they work. So have someone read it and perform the task, and this is perfect for a new employee. Keep a date on there when it was last revised, and plan to review them periodically. Once a year is preferred.
Here's an example of an excellent SOP. It's a laminated card. This is from Tacoma's water treatment plant. They have this laminated card at each device. It's awesome. So it's clear what the instrument is. Here's the serial number for the instrument. And then they have different settings, the values, and then the best part I like is here's how you get through the menu. Here they have the date of their last primary calibration and the date of when they last replaced the bulb. It's right there at the device. Here's some turbidimeter setup. So this actually is picture on the left is from a Great Lakes manual, and it's awesome. Once again, they have columns, and here's great is they leave this column for you to put in what you think or what you're going to use at your plant. This particular plant didn't actually use that great feature, but it's there. You can also, if this is a smaller plant, they put their settings right on the front of the paper manual. So different ways to go, some better than others. We have talked about turbidity measurements and the instruments and human factors. Data accuracy also involves reporting values to others or transferring that data. So in Washington State, we require that the CFE, combined filter effluent, be reported to us at 4-hour intervals. So here's an example of a filter run. This is CFE data, and they start their filter run at 3 o'clock or 1500 hours. And within the first 15 minutes, they're supposed to get a reading. And that's what this yellow spot is here. So turbidity drops down at 1515, they record that value. There's a little bit of a turbidity spike, and then the filter run settles in and runs, for the most part, pretty well. There's some anomalies in it, and 4 hours later at 1915 is the next 4-hour reading. The daily max in Washington State is supposed to be just that, the absolute maximum turbidity value from the CFD. In this case, it looks like this filter ran past breakthrough, and now they're going to capture it. They're running at this before they take the filter offline to backwash. So there's a higher spot here when you first come on. There's some blips, but this is what we require. We found that 40% of water systems were reporting the 4-hour readings incorrectly. Some set a set point. They would set their turbidimeters, okay, when you hit 0.2, trigger that first one. So some of these might actually be an hour or more after filter startup instead of the first 15 minutes. 44% of the systems were not reporting the required absolute maximum for the day. The most common mistake here was to report the highest of the 4-hour readings. One water system was using the average of the 4-hour readings as the maximum for the day. I want to give another example. Here is a turbidity output from a plant operating 24 hours a day. You can see from midnight to midnight. In this case, this plant is measuring at 4-hour readings all the time. So midnight, 4, 8, etc. And correctly, they supposed to pick the absolute largest, highest turbidity value for the day. Reporting requirements may differ by state. So this issue, really you have to know what your state requires for this.
So we did encounter, infrequently, but we found a few data recording issues. So at 3 systems, the SCADA or the recorder did not match the online instrument reading. So keep in mind that the scale that you set in the controller has to match the scale of the recorder in SCADA. So when you replace a device, change settings, you need to calibrate SCADA with the controller output. So I want to show you just a simple example for how this works so you can kind of get it in your head. I needed this. This is a finished water turbidimeter, and it's set with a signal span of 0 to 1.
So that's actually, we would rather see 0 to 5.
Right, but this is how they were when we found them. And the SCADA was also set up that way, so it was matched. So this system had a regulatory violation. It exceeded 0.3 NTU. So this was converted to a milliamp signal, 9.6, which SCADA properly interpreted as 0.35 NTU. So after our visit, let's say, the operator decided, oh, I need to change to 0 to 5, but the operator only changed the controller, didn't change SCADA. So here's what might happen there. Instead of a 9.6 milliamp signal, the controller would send 5.12 milliamps. And now the SCADA, instead of picking up a 0.35 NTU, it's a 0.29 NTU. So no regulatory violation detected there.
Continuing on with recording issues, had not just they don't match, but we had 3 systems where the recording device was broken or inoperable, so it might have just been missing. So that's pretty significant. In this case, data integrity in these settings is suspect. The turbidity data reported was based on visual readings of online instruments by the operator during the course of the filter runs. Just a little plug, that is a 1720B, and that was operating a treatment plant up until 2012. So they definitely got their money out of that one. So some tips here, looking at the online analyzer installation. We want to get a representative sample location. So there's a lot of things affecting data integrity. We're looking for turbidity in this case to represent filtration performance primarily, not filtration and additional setting or clarification occurring, say, downstream of the filters after the clear well. So the location that we pick is a significant issue. Tapping the side of the pipe is clearly recommended over the bottom where you may get sediment, but even more importantly than the top of the pipe where you tend to get air accumulations, which can lead to some erroneous turbidity readings. If you can, it's ideal to avoid pumping. That's not always an option for people. Don't want to mix and match dissimilar metals. So this is a real example here. You can see that's pretty occluded. I don't want to get the opinion that we don't think being frugal is good, but it's where we're saving the money. So some of the tubing we've seen is amazing, maybe never replaced. It's relatively cheap, and that can have a big impact on the quality of the water that you're sending to your turbidimeter. And you should consider sample delay. So we're going to talk a little bit more about that.
Yeah, so sample delay. This is from an actual treatment plant, and it's an example of what you don't want to have. So you take a look at this. This was a plant that had been retrofit, so putting some new into an old box, so that made it a little hard. Filter number 4 had 24 feet of, I think that's ½ inch tubing. They'd been having trouble with bubbles, so they put in this big bubble trap, 3 foot high, 4 inches in diameter, and the flow rate was only 114 mils per minute, so it was actually below the range that was specified for that turbidimeter. That turns out to be a 70-minute delay. So if they had a critical alarm attached to that, you can imagine by the time the alarm went off, the water would already have been 1 hour away. So here's a tip. Use short, small diameter sample lines. Aim for a sample delay of no more than a minute if you can. You want the smallest tubing that can deliver the flow you need, and high velocities will help keep biofilm from accumulating in those lines. So other issues, this could have actually been 10 slides, because the more you dig into the issues around turbidity, the more things that you find that are important. So this is a kind of laundry list. I want to highlight a few. In Alabama, the drinking water program there alerted us to the fact that some of the photocells out there were damaged. They were losing the protective oil that was in the photo detector, and so when you turn those on their side, you don't see the normal bubble and that can mean that the photocell will be less reliable going on. So they contacted the manufacturer and learned that those should be replaced if you find that the bubble is not present. Looking at power supply, we had a number of utilities where the weekly test of their generator would wreak havoc on their equipment. And so many of them installed uninterruptible power supply. But these vary all over the map. The one that's shown here is a $70 model that you can buy at the office supply store. And I think the point here is that this is much different than a system that costs 100 times as much that has a lot greater capability. So if you decide to pursue this, I would definitely talk to people who are experts in this area and make sure you're buying the kind of protection that you're looking for. A third one I labeled maintenance pitfalls. We've seen this at a number of plants where the flow gets interrupted to the turbidimeter, maybe during maintenance, and not restored when the the system goes back online, or the instrument is placed into hold mode for calibration, and then they forget to take it out, so it remains in hold mode. And sometimes this can happen for, you know, a weekend. It always seems like it happens on the Friday. So maintenance pitfalls and SOPs and operator training, those are the solutions to that one. Another one I called hidden data manipulation, and recently we heard from a utility that had the controllers actually lock up. They didn't realize it, but their alarm testing procedure caused the controller to go into a hold mode. And it was only when they started looking really closely at the data during an optimization exercise that they realized they were getting a flat line from those individual turbidimeters. So I think they solved that by, number one, changing their alarm testing protocol, but they also put an alarm on there to look at that fourth or fifth decimal place of the milliamp signal and tell them, you know, if it hadn't changed for 2 minutes or so, they get an alert that they can follow up on. So I think you'll find, as you look at turbidity more, you'll probably add to this list. So if you'd like to learn more, we published a paper on turbidity data verification back in December of 2014. You can certainly read that article. There's also an article written by Terry Engelhardt of Hawk Plumbing Sample to a Process Analyzer. And I gave you a reference there. If you search that publication, you'll find it. That's very good. And then we put together some guidance on what we think settings should be for turbidimeters. And I gave you the publication name and number there. You can get that on our website. This is a summary of those settings. And I think, you know, we've covered a lot of ground here. I think it would be good to just talk about what we think are the highest priority settings to be looking at. So the first one is kind of obvious, but yes, you need a data recorder, and it needs to be calibrated to the output of the controller.
Signal span, we think that 0 to 5 NTU for finished water is a good balance between not capping and data resolution, and from what outputs we would expect.
The error mode is a really important thing. If you have any controllers that have this setting, make sure you know how they're set. Make sure they're not holding the last good reading.
And last on the top 4 is you have to have written SOPs for your turbidimeter settings, so all the staff know what they are and you can replicate that. We've been talking about online instruments, but boy, you cannot escape the power of the online world, the World Wide Web. There's so much information there. I have kids, and they no longer look at books, they just go to their devices. So here's an example. This particular training video is excellent, and there are many things like that on the web. We can't say enough about the staff members at the 25 surveyed water treatment plants, who without exception welcome this opportunity to teach us to learn and to improve operations. So the 25 utilities are listed here, the whole spectrum. Once again, can't thank them enough. We kind of come back at the 59-minute mark, I might note. Wow, for accuracy. Questions and feedback, but we have a question to the general audience, and that is, it's almost like a dilemma, some ancient Chinese quandary to test our Jedi Knight abilities. So how do you provide effective training to all practitioners in our world? Data integrity depends on way more than just operators at treatment plants. Instrument manufacturers, their instructions really set the tone. Designers, so the design engineers or techs, both physical sampling and workstations. I can't tell you how difficult it is just to measure flow rate when you have to get down on your knees and reach under a pipe gallery to check the accuracy of the device. You gave examples there of Tacoma's laminated card. These things make a big difference. So in the course of this, and don't forget health departments, regulatory agencies, what are our expectations? How do we model, essentially walk the talk, if you will? So in addition to any questions you have, if you have any insights, we would sure welcome them. And that concludes.
Thanks. So it looks like we have one question here. Someone is asking if we recommend a specific type of benchtop turbidimeter to use. They asked about some models, let's see, the 2100P, the 2100Q versus the N series, which do you find more accurate? So I have to tell you that since we do field work, we use a portable. So we don't have a lot of experience with the laboratory style. But one thing we do notice is if you have an older unit, like the Ps are pretty old now, that they just don't, people have a lot of trouble getting a good verification. We've had systems with a P by a Q, and then suddenly the problems went away. Yeah, so we actually have a 2100Q, and it seems to work fine for us in that setting where we're going out into the field.
And we have been able to match online instruments with the 2100Q with the best technique. It really has to have great technique.
Yeah, now here's a question. Did you develop or find a preferred protocol for sample acidification downstream of lime softening, if that is applicable to your system?
We did not. We do not have any lime softening plants.
Not a single one.
In the whole state. So we have nothing for you on that.
Questions? Your thoughts on the new self-cleaning turbidity analyzers, good or bad? So perhaps you're referring to there's a new Hawk TU5 series, and we have just one utility in the state that's really incorporated that so far. And they've been great about sharing information with both us and other utilities. I know a lot of operators have gone to visit them. What I've picked up from that is that there's some differences with what you've been used to. There's a different method of calibration. It's a sealed standard instead of a liquid that you pour into the body. Condensation is important. So this turbidimeter has a method to remove condensation internal, but when you open it up to do maintenance, it takes a while for it to catch up. So this utility has put a delay on the signal. I don't remember exactly what it is, maybe 90 seconds to account for that. And the third thing is there's a optional flow sensor, which I think should not be optional because it allows you to connect an alarm that can tell you either if flow is interrupted or if you're outside of the specified range. So that seems like it shouldn't be optional. And then the last thing that actually gets to the question is the self-cleaning. I think it comes with an optional self-cleaning, and I don't really know how those work. I know you have to give it a frequency. How often do you want it to do it? And so I'm not sure, what happens if you don't put it on there. I haven't seen this out there enough.
And when we only have one really with operating experience, you don't really have something to compare it to.
But I think the lesson learned here is if you're going to switch to a different kind of equipment, go and visit plants that already have put it into place and take advantage of their lessons learned. so that you don't have to. I think, you know, one of the things with the error hold mode, the reason so many people didn't see that coming is when they upgraded from the 1720D to the E and they added that separate controller. The controller now was intended to handle a lot of different sensors, not just turbidity, and so the defaults were like different from what we were all used to. So if you've been running along with the D and you just upgraded without thinking about it, you would have missed that totally.
Yeah. The next question, would you change any of your recommendations for raw surface water tap locations? Oh, skipping it, sorry. We found that setting the turbidity alarm at the highest range, 5 NTU, failed to set off the turbidity alarm as the alarm could not read above the analyzer. Have you come across a similar surface? So if I'm understanding that, you set it at 5 and it's, or 5.0 and it's capped at 5, so it never exceeded it. I don't.
Where it happened?
Yeah.
Where capping actually happened?
And didn't sound the alarm.
Oh. Failed to set up the alarm. Huh. I haven't heard of that happening, but that doesn't mean it hasn't happened.
Yeah.
I kind of think we need a forum for these sorts of things, kind of apart from, you know, the manufacturer, but where people can post their experiences and questions, and I think that would be really helpful.
Yeah. Would you change any of your recommendations for raw surface water tap locations associated with LT2, crypto, or E. coli monitoring or similar risk analysis?
So if you're referring to like signal span, you want to set the raw water to be to cover the entire range of what you expect to see. So if you expect to see 1,000 turbidity units, you better get a turbidimeter that can handle that, and you probably don't want to cap the data.
Right. Absolutely. And generally, you want raw water before sedimentation or anything else. So that could be something at play. You might also have a turbidimeter between sedimentation and your filters, and that might then be expecting to see way less turbidity.
So here's a question, Steve. How do you deal with operational spikes in the treatment train when reporting the highest CFE value in a 4-hour block? Can a system exclude a value if it's something like plant startup, power flash, backwash of another filter, etc.?
Well, I'll take this one.
Okay, go.
Yeah. So within this, remember they're reporting at 4-hour intervals, so those should just be what they are. So really what we're talking about is the maximum for the filter run or for the filter day. This would be where if you have your frequency at not 6 seconds, you're going to have problems. So if you dampen it with a 30 seconds, hopefully that will attenuate those spikes. If it represents the turbidity that's happening, you should report that. If this is something that's different, then in our opinion, you would document that on your monthly report. Usually there's a comment section. We would prefer that once you have that, you would call our office and discuss it with our regional engineer.
So for example, if someone was visiting your plant, you were giving them a tour and they ran into the turbidity sensor and it caused a spike, well, that's not a real spike. So that one you would document in an excursion log and you would report that as a regulatory value. But you need to be really careful about that you really are just excluding the ones that are not true readings. I don't see any other questions. Let's just wait a minute and see if there's any that are being typed just for a second. Okay, here's one.
We have a Hawk service agreement contract where they service our turbidimeters and other equipment every quarter. All bulbs replaced, etc. Do you see a need for maintenance more often than this?
So as we mentioned in our state, we we require utilities to do a verification every week. So that would be in addition. Some utilities have, for whatever reason, more buildup in even their finished water turbidimeters, and so they have to do some flushing there.
Other things that may or may not be included in your service contract would be replacing the sampling tubing. And no matter if Hawk does it or your staff do it, we think that all of these maintenance activities should be documented in an instrument-specific maintenance log. I can't remember if we talked about that, but lots of plants, especially the smaller plants, keep a general maintenance log of everything they do. Those are valuable, but those are difficult if you're trying to find out a specific question on a specific piece of equipment, like the last time the tubing was replaced.
And one of the systems that we went to had multiple filters, and their turbidimeters were not all within the specified range. They had a Hawk service contract, so they don't always cover everything, such as sample flow rate.
So this comes back to our big push on SOPs. And in your SOPs is still, here's what should be done to each instrument. Here's how we maintain it. Who does it? That's kind of up to each utility, whether you do it contracted out or you have your own staff.
Okay, the next question is the 4-hour measurement an average, for example, 30 seconds, or an instantaneous measurement? So that's going to be, it's really a snapshot of what you see on your SCADA. Clearly, if you have signal averaging, which we hope you do, it's going to be a 30-second average or something like that. But it's not otherwise manipulated.
Yep. Do you have recommendations on how plants should set up their SCADA systems to differentiate between valid turbidity readings and those taken during other time periods, like doing filter backwashes or closer to waste time periods, etc.?
Yeah, so you definitely need that, and often having the valve position shown on SCADA along with the turbidity display will allow you to visually see that. I'm not a SCADA expert by any means, but you definitely need to be able to exclude those times when the filter is not actually in service.
We have some comments.
Yeah, excellent webinar and information. Thank you. You're very welcome.
Can we get a copy of this PowerPoint sent to us by email? Anthony's going to come back and talk to that, and if they can't, then you could just send us an email inquiry. Email address is listed, and we can send it.
And here's another comment. In Tennessee, systems have to verify their combined filter effluent turbidity meters every day.
Okay.
So that's really interesting. Well, great questions and feedback. We really appreciate it.
All right, so last 30 seconds on any questions. We could even push it to 45, but any other questions? We sure appreciate your time and efforts improving data integrity. And Anthony, I guess we'll head back to you.
All right, gang. Thanks so much for the presentation. Thanks, everybody, for sticking around. We have recorded this session, and like I said, it'll be available on the ASDA website probably sometime tomorrow morning in the past events section. If you need a copy of the slides or any of that information, you could email me. My email address is aderosa@asda.org. And we will see you on the next call. Thanks, everyone, for joining.